Introduction to electricity. Electrical circuits. This is a system of conductors and components forming a complete path for current to travel. There are different properties of an electrical circuit. One of those is voltage, another is current, another is resistance. Voltage is measured in volts, current is measured in amps, and resistance is measured in ohms. Ohm's law. Current in a resistor varies in direct proportion to the voltage applied to it and is inversely proportional to the resistor's value. All those confusing words can be summed up with this nice little equation. Volts equals current times resistance. For whatever reason, the letter used in this formula for current is an I. I don't know why, but that's just the way it is. So here we have this nice table. We have the names, the abbreviations used in the formula, what units they're measured in, and the symbols. Example of Ohm's law. The flashlight shown uses 6-volt battery. Here's the symbol for battery. We have here voltage total equals 6 volts. And has a bulb with a resistance of 150 ohms. This symbol here means we have a component here. In this case it's a light bulb. And it has 150 ohms is the resistance at this point. When the flashlight is on, how much current will be drawn from the battery? Using Ohm's law, we could say that the volts equals the current times the resistance. Using these little subscript T's here for saying the totals, total volts, total current, total resistance. In this particular problem, there's only one of each of those things. But on other problems, there are more than those, and maybe you're finding voltage, current, or resistance at certain values. If you're doing the total system, I would use these subscript T's. Our volts here are 6, so we're going to replace this with 6. Our current, we don't know. So we're trying to figure out how much current is being drawn. The resistance, we have 150 ohms. This is supposed to be the symbol for ohms, which I drew poorly just now. Using algebra, trying to get I by itself, we divide both sides by 150 ohms, and we get 6 volts divided by 150 ohms equals the total current. If you put that in your calculator, you're going to get 0.04. This is in current, so we're supposed to label it with an A for amps. Typically, if your amps is less than 1, in this case we have 4/100ths of an amp, you would convert that to milliamps. To do so, multiply this number by 1,000. There's a decimal place 4 places, and we get 40 milliamps. So that is the total current going through this battery. Circuit configuration. There are 2 versions of circuits. There's a series circuit, and if you follow this, you can see there's only one path for electricity to flow. You have a parallel circuit, which as you go down through here, you have choices. We can come back up and around, or we can go to the second one and around, or the third one and around. The biggest difference you'll see here in a series circuit, if I remove one of these items, my path cannot reach back to its original destination. There wouldn't be a complete path. In a parallel circuit, if I remove one of these items, I could still have a complete path for the other items that are in here, except for the one that I removed. Kirchhoff's laws, and I'm not sure if I'm pronouncing his name correctly. Kirchhoff's voltage law. The sum of all voltage drops in a series circuit equals the total applied voltage. Here's what that means. The voltage of the total circuit is going to equal the sum of all the individual resistors. And let's say that we have n resistors in this case, so we're continuing to add until we get to the nth one. So in this specific picture, if we had 4 resistors, if we added up the resistance at each of those, that would equal the total resistance in this system. Kirchhoff's current law. The total current in a parallel circuit equals the sum of the individual branches of each current. So the total current is going to equal the current at each resistor, each component, if you will. Let's say once again that we had n of those. In this specific picture, there's 4 of them. Add up the current at each 4 of these things, and that's the total current in this circuit. Series circuits. Characteristics of a series circuit. So these are facts about every series circuit. Fact 1, the current flowing through each series component is equal. So the current here is equal to the current here, which is equal to the current here, which is equal to the current here, which is equal to the total current, each of those individually. Fact 2, the total resistance is equal to the sum of each resistor. So if I add up the resistance of each of these resistors, it's going to be the total. And the third fact is Kirchhoff's voltage law. The total voltage, in this case it's 12 volts, is going to equal the sum of the voltage at each of these components. If I add this one and this one and this one together, it's going to equal the total volts. Here's an example. We're going to find several things. From this picture, we're going to find the total resistance, the current at each of these components and the total. We're going to find the volts at each component and the total volts. And then we're going to verify Kirchhoff's voltage law. Second part to this, let's find the current at each of these components. I means current, and let's find the total current. Let's first find the total current. The total voltage equals the current of the total times the total resistance. So we can see here in our picture the total volts is 12. It's clear, it says 12 volts. That means this is the battery here. The total current is what we're trying to find. We don't know what that is, so we're just going to put an I sub t. And then the total resistance, we just found that out in the previous problem, which is 1890 ohms. 1890. If we divide both sides by 1890 to get I by itself using algebra, and put this into our calculator, you will find this comes out to be 0.0063 amps. Remember that current, I, is measured in amps. To convert that to a number that's bigger than 1, if we multiply that by 1,000, we get 6.3 milliamps. So the total resistance, the total current, 6.3 milliamps. Please note, in a series circuit, which this is, the total current is equal to the current at each component. So what does that mean? Let me write that down first of all. This was a fact on the previous slide. Current of the total is equal to the current at each component. And since we just found out the total current was 6.3 milliamps, we could say that all these things up here are all equal to 6.3 milliamps. Each component is 6.3 milliamps. Supposed to find now the voltage, the total, and then the voltage across each component. Well, we know what the total voltage is. It is clearly, right here, 12 volts, so that requires little to no effort. Now let's do the voltage across each component. Let's take the voltage at component 1. So we're saying the R is the resistor. Each component in this, with the exception of the battery, is called a resistor. Could be a light, the resistor. Could be an actual resistor. Could be a switch of some sort. Those are all called resistors as far as I know. That's equal to I times R. So I is the current at that resistor, and R is the resistance at that resistor. So we're just looking at the first resistor, which is this one right here. So the volts we don't know. The current we just figured out. When we put this into the formula, let's use the amps. Let's not use the milliamps. It's 0.0063 amps. And the resistance picture shows is 220 ohms. If you multiply those out using a calculator, you're going to find that it's 1.4 approximately volts. If we do this similarly with the second resistor, volts equals current times resistance. And we are speaking specifically about the second resistor here, so we write subscripts for those. The volts we don't know. The current is the same in each resistor, and that's because of Kirchhoff's current law. No, it's not because of Kirchhoff's current law. But in a series circuit, the current is the same across each component, which was 0.0063 amps. And the resistance here, we can see in this picture, 470 ohms. Sorry once again for the ugliness of my ohms. Multiplying those together, you would get approximately 3 volts. And then finally the third one, third component, volts equals current times resistance. Volts we don't know. Current is the same at each component in a series. And the resistance we can see here is 1,200 ohms. Multiplying that out, it comes out to be approximately 7.6 volts using a calculator. So we were supposed to figure out total volts, which we did, across the first component, across the second component, and across the third component. Done it, done it, done it. Verify Kirchhoff's voltage law. The voltage law says that the total volts is going to equal the volts across each resistor. Pardon me. The total volts is going to equal the current summed. Sorry, I said current. Let me start over. The total volts is going to equal the volts across each component. We have 3 components here. So we can see the total is supposed to be 12. Resistance, the volt at the first component we just figured out was 1.4 volts. We just figured out that the resistance across the second one was 3. And the last one we just figured out was 7.6. If you sum those, you get that 12 volts equals 12 volts. Thus, verifying for this specific problem, Kirchhoff's voltage law is correct. Parallel circuits. Circuit that contains more than one path for the current to flow. In this specific picture, we got this battery and we got 2 light bulbs. If I were to remove one of these light bulbs, the other light bulb would still work. If I had to remove the first light bulb, the second one would still work. That's how a parallel circuit works. Facts about parallel circuits. Compare these to the facts of a series circuit. Fact 1, the voltage across every parallel component is equal. So if this is 15 volts, this is 15 volts, this is 15 volts, this is 15 volts. They're all 15 volts. In a series circuit, whatever this total was, if you added up each component together, those sum to be the total. But here in a parallel, whatever the total volts are, that's what it is for each component. To find the resistance, this is a hot mess, and this plus sign should not be there. You basically take 1 and divide it by the reciprocal of the resistance at each component. It's a hot mess. And then finally, the third fact, if you take the total current, I's current once again, if you take the total current, it's equal to the sum of the current at each component. That's Kirchhoff's current law. So here's an example of a parallel circuit. We want to find the total resistance. We want to find the volts across each component. We want to find the current that's going through each component. And we want to take our results and verify Kirchhoff's current law. Let's first find the total resistance. Finding the total resistance here, not as simple as we would like it to be. The formula here is going to be the total resistance is going to be 1 divided by the reciprocal of each resistance at each of these components. We have 1, 2, 3 components and a power source. So we're going to have 1 divided by R sub 1 plus 1 divided by R sub 2 plus 1 divided by R sub 3. So, R sub 1. R sub 1 is 470 ohms. R sub 2, 2.2 kilo ohms, which will change to 2,200 ohms. These units have to be consistent when you write them into these formulas. And then finally we have 3.3 kilo ohms, which is 3,300 ohms. Now if we were going to show all of our work algebraically, how to simplify this fraction, that would be a mess. We're not going to do that. Just put this in your calculator, making sure when you do, you put each of these fractions in parentheses. No, I don't want to say that. I want to say take the entire denominator and put it in parentheses when you put it in your calculator. So stop this, put it in your calculator, and see if you do it correctly. Here's what you should get. You should get the resistance of the total circuit. It's 346.6 ohms. If you didn't get that and you need help with your calculator, let me know. So I'm supposed to find that, and we have done so. Now we're supposed to find the voltage, the total, and then we're supposed to find the voltage across each component. Well, fortunately for us, In every parallel circuit, the total voltage is equal to the voltage at each resistor, each component. They're all the same. And for this particular problem, we can see this battery, this power source here, it's 15 volts. So they're all the same, they're all 15 volts. Now let's find the current through each of these components. Well, we've just figured out that that the volts is 15. I'm just going to write that down. And that's the same across each component. So let's say that we want to find, first of all, the total current. Using Ohm's law. Volts equals current times resistance. So I'm doing totals first, so my subscript is totals. So the volts we know is 15. The current we do not know. The resistance we found on the previous question on the same problem was 346.6 ohms. And if you divide both sides by 346.6 ohms, to get our total current, using a calculator, it ends up being 0.0433 amps. That's what current is measured in, as amps, which is 43.3 milliamps. So that's the total voltage. Pardon me, that's the total current. That's what we're trying to find there. Now we need to do the same thing 3 more times. We need to find it for each of the other components. So let's see if we can find the volts at the first resistor. Volts equals current times resistance. Total volts is 15. It's 15 for all the volts of each of these components. This current we don't know. Try to simplify our work a little bit here to avoid so much writing. The resistance at this component here is 470. Trying to get I by itself, so we're going to divide both sides by 470 ohms. It's going to divide the left and the right side. Put that in your calculator. That ends up being 0.032 amps, which is about, well, it is 32 milliamps. I gotta do this 2 more times now. Let's find the current at the second component. So the volts at the second component is going to equal the current times the resistance. Volts is 15. Current, we don't know. The resistance, 2.2 kiloohms, which is 2,200 ohms. Divide both sides by 2,200 ohms using algebra to get I by itself. It comes out to be 0.0068 amps, which is 6.8 milliamps. And finally, the last component here, resistor 3, same formula, Ohm's Law. Ohm's Law is not going anywhere, boys and girls. It is here for the long haul. The resistance at the third resistor is 3.3 kiloohms, which is 3,300 ohms. Divide both sides by that to get I by itself, and you get 0.0045 amps. Which is 4.5 milliamps. So we just found the current that goes through each component, and we found the total current. Verify Kirchhoff's current law. The current law once again says the following. The total current is going to equal the current across each component. I said that wrong again, I'm sorry. The total current equals the sum of the current across each component. So we figured out that the total current was about 43.3 milliamps. We were rounding. Resistor 1 was 32 milliamps. Resistor 2, its current was 6.8 milliamps. And resistor 3's current was 4.5 milliamps. If you sum those on the right, you end up with 43.3. which is what the left was all along. So this verifies, for this problem, Kirchhoff's current law appears to be working. Finally, electrical power. Power equals current times volts, and that is measured in watts.